Okay, the topic of this video is refraction at a convex surface, and we'll look at a case of when a ray of light is traveling from a rarer medium to denser medium. That means the ray is traveling from probably air into the or onto the convex surface. So before I share with you the objective of this video, let me first draw a convex surface, and let us say this is the convex surface that we are looking at, and let us say this is the principal axis. I am using a different pen over here so that I am able to draw sharp lines and able to show angles very clearly. Maybe this is the principal axis of this particular object, and as you know, this will be point P, and let us say a ray is incident on this convex surface. Now, in case of convex lens, we know there are two possibilities. The image could be real or virtual. So let's first take the case of, let's say, the real image. And when we have real image, the object is, let us say, far away from this. So let us say this is the object O over here. If it is incident on this particular point, I need to show the normal over here. So let us say this is the normal over here at this location, and you know this point will be the center of curvature. I don't want to get into the reasons why this is center of curvature. We have discussed that in an earlier video. Refer to that to see why this is center of curvature. Ray which starts from the center of a sphere is perpendicular on the surface of the sphere, and this is perpendicular over here, therefore center of curvature. And let us say this is a ray is incident at this location, so this is the incident over here, this is the incident. Let us call this point A over here. Now the objective of this video is to look at this case in depth, look at various angles involved, and arrive at a relationship between mu1, mu2, u, v and r. Right. This is air, this is the rarer medium. Let us say it has refractive index u1. This is the denser medium, which is the convex lens in this case. Let us say its refractive index is mu2. So mu1 and mu2. U and v you know are distances of object and image, and r is the radius of curvature. Radius of curvature is the distance from the pole to the center of curvature. So we will try to arrive at a relationship between these parameters. Okay. So let's proceed. So this is the incident ray we have shown over here. This is the normal over here. So this will represent the angle of incidence. Now it is traveling from rarer to denser medium, so it will bend away from bend towards the normal. So this is how it would have. This is how it would have traveled further. It will bend towards the normal. So it will. Let me extend this line a little bit over here. Probably. And let us say it's bending towards the normal, so it goes something like this. And the image gets formed over here after refraction. So this is the refracted ray. If this is the refracted ray and this is the normal, this will represent R, which is the angle of refraction. Okay. Now let me drop a perpendicular from here, and let us call this point M. So we have angle of incidence and we have angle of refraction. Let us identify a few more angles. Let us say the angle, this angle with the point of the object is alpha, with the image beta, and this is gamma. And the reason why we are taking these angles is because we are trying to find a relationship between u, v and r in this. And this O represents the object, I represents image, and this represents r, the radius of curvature. So we have now three more angles, alpha, gamma and beta, and we also have I and r. Now here we will be using a little bit of our knowledge of geometry. We know that if we have a triangle, let us say this is a triangle, and let us call this angle ABC. Let us say this is angle A, this is angle C. Right now, if I draw a line over here, right, then we know that the external angle, this external angle will be equal to the sum of the opposite internal angles, AC. So this is one concept which you would have studied in geometry. We'll be using that concept over here. the sum of two internal angles is equal to the external angles on the opposite side. Right? So let us first look at triangle, say for example triangle OAC. Triangle OAC. So the triangle that I am referring to is this triangle. Triangle OAC. Now what do we see in this case? What we see in this case is that in this triangle, gamma and alpha are the internal angles. Gamma and are the internal angles. Right? And what is the external angle that we are looking? What is the external angle we are looking at? Now, if this is angle I, right? We are looking at angle OAC. Right? This angle. So you can very clearly see I is this is gamma, this is alpha, and the external angle is I. If I extend this line over here, this line is getting extended over here. So external angle is I, and therefore I can write down that in triangle OAC, I is equal to alpha plus gamma. That's one. Okay, if I look at triangle IAC, so which triangle I'm referring to, triangle I, A, and C. In this case, the internal angles are beta and R, which is angle of refraction, and the external angle is, as you can see over here, gamma. B and R are the internal angles and gamma is the external angle. So in this case, I'll write down gamma is equal to R plus beta. Gamma is equal to R plus beta. We'll have to be very, very careful with these symbols. I'll show gamma as this and R as this. Right? And therefore, I can write down I is equal to alpha plus gamma and R is equal to gamma minus beta. Now, what is alpha? If you look at angle alpha I can write down is equal to AM upon MO plus what is gamma? Gamma is equal to AM upon, this is gamma. Gamma is equal to MC. And you know what we have done? We have assumed that these two angles are very, very small, and therefore the angle is equal to opposite side upon, right, upon the adjacent side. Right? So we have taken tan of these two angles, and as we discussed in the convention, when we discussed conventions, we said that sine theta is equal to tan theta is equal to theta. So that's what we have done. This angle is equal to tan theta. Tan theta is equal to opposite side upon adjacent side. So AM upon MO plus M upon MC. Now we will write AM upon what is MO. This is M, this is O. Now MO can be taken as PO or OP plus AM upon MC can be taken as PC. Right, I is equal to this. So this will give me AM into bracket common 1 upon OP. Now OP is, we know, is the distance of the object. And what is its convention? Is it positive or negative? This is the direction of angle of incidence. PO is in this direction, therefore it will have negative sign, so I'll write down 1 upon minus U plus 1 upon PC. PC is in the same direction as the direction of image, so I'll get. So this is I. Similarly, I'll look at R. R is equal to gamma minus beta. Now what is gamma? Gamma will be equal to AM upon MC minus beta is equal to, where is beta? Beta is this. Beta will be equal to AM upon MI is equal to AM common 1 upon MC. Now MC can be taken as equal to PC minus 1 upon MI can be taken as equal to PI 1 upon M. What is PC? PC is R, right? And what is the direction of R? From P it is going in this direction, same as angle direction of ray of incidence. So 1 upon R minus 1 upon PI. PI is this same direction, so, and that is distance of image, so positive sign 1 upon. So I have got now an equation for I and R. Now by Snell's law, mu2 upon mu1 is equal to sin I upon sin R. Refractive index of the second medium with reference to the first medium is sin I upon sin R is equal to I upon R because angles are very, very small. So if I take mu2 into r is equal to mu1 into I. Right. So mu2 into r. What is r? R we have obtained is am into 1 upon r minus 1 upon v is equal to mu1 into what is I? I is am into 1 upon minus u plus 1 upon v. am will get cancelled, so you'll get mu2 upon r minus mu2 upon v. I'm opening this bracket, multiplying mu2 to 1 upon r and 1 upon v is equal to mu1 upon minus u plus mu1 upon v. And if I rearrange this, in such a way that I get mu2 minus mu1. Let us say we are having, this is mu1, mu2 upon mu1. This is r minus v over here, so I will take mu2 upon mu1, so I'll take is equal to mu1 upon minus u. I'll shift this on this side, so I'll get plus mu2 upon v is equal to mu2 upon r minus mu1 upon r. Therefore, mu2 minus mu1 upon r is equal to mu1 upon minus u plus mu2 upon v. And this is the relationship that we are looking at, relationship between mu1, mu2, u, v and r. So this is how we get, in fact, this is, if you look at this is OP. What is OP? OP is the distance of the object. This is am upon PC. What is PC? PC is r. So this should not be, this has to be r. So that's a small mistake I did. I think we'll make that correction over here. So this is 1 upon r. So where we have multiplied I, this will be r. This is r. And this is how we get 2 r's over here. And so I made that small correction, that small error which I committed, I made that correction over here. And finally we get this relationship between the refractive indexes, the distance of the object and image, and the radius of curvature. So this is how we handle the case of convex surface when we have a real image. I would like to try on our own what would happen in case of a virtual image, right? And the method will be very, very similar. The only thing is that the image will be virtual, so the object will be very, very close over here. What I would recommend is that you put the object over here and do the same exercise similarly, and you will come back to this particular equation. I'll be doing a video on that, right? But before you have a look at the video, I strongly recommend that you try that on your own. Thank you.